Everyone, welcome to another day of neural network training. Today, I'm your instructor Arnav Bhute, and special credit to Andrew Ngee for his deep learning specialization course on Coursera. And today, we get started on backpropagation, which is, last video we did forward propagation. This video we're covering backpropagation, and with this, we will understand how a neural network really works. So, the fundamental idea to backpropagation is loss functions. These are mathematical functions that quantify the difference in the predicted output of a neural network and the actual output. So, for example, how similar is an image to what the model outputted compared to what the actual image is, or the ground truth? Or, within another example, how similar is the value that the neural network predicted as to be the value of, for example, how much dice is going to be worth compared to what actually happened? And we have to identify those differences and see if the model is training or not. Loss functions quantify that difference, and we can see in how to improve that loss function, obviously right here. So here we can see the loss function on the training data. It was pretty convergent, very nice, smooth. On the test data, though, it wasn't as nice, and it seemed pretty shaky while it was training this model here. Clearly, you can see this model could probably use a little more improvements, and most likely overfit it on the training data, which is why it had such good loss, while the test data simply wasn't at that level. Considering that, it's pretty easy to see that everything comes down to the loss function. In backpropagation, we calculate the slope of the cost function, and we use those to change the weights, because remember, the weights of a neural network, W and B, make all the difference in how the model predicts, and so we have to optimize those weights. For that, we use the gradient descent algorithm. We find optimal weights between layers that decreases this cost and loss function to the left. We'll get into the specifics right here in just a second, but just remember, loss functions make up backpropagation, and we want to optimize those loss functions. That's why we use gradient descent. So on to the logistic regression cost function. Essentially, if you remember from forward propagation, you have the probability of y, or the probability of something being 0 or 1. This is for logistic regression. And essentially, that is the activation function times W transpose X plus B. Then you apply an activation function like the sigmoid function and fit that data to give you a probability. Here we can understand that obviously W transpose and B are the two parameters we are trying to optimize. And the typical loss function looks as L, parentheses, y hat, and y. Essentially, it's 1/2 parentheses y hat minus y squared. We don't have to do too much of the mathematics, because in actual coding, we will see that you can just use the name of the function without really having to type all the formulas without it. But essentially, that's what we see as a loss function. Now, back here, we did cover the cost function, which is essentially what is used to optimize and change the weights. And that's exactly what happens here. So loss function is only for one example. Let's say you have an example of 500 types. How do you combine all of those loss functions into one function so you identify how well the model is actually doing? That's where the cost function comes in. It's defined as JWB. And basically, you just take the average of all of these loss functions together. If you know a little bit of calculus, this is essentially an integral that's being used to find the average of something that's accumulating change. And precisely just like that, we are using the cost function to combine all of the loss functions across all the training types into one quantitative data frame that we can train on. Essentially, let's recap. Loss functions and cost functions are the same thing, except the cost functions are a list of loss functions, and loss functions are just for one training example, while cost functions can go for any I number of training samples, as detailed here. So, between cost and loss, it's important to identify the importance, but then we have to identify what gradient descent really is. I just touched on that right here, that gradient descent is used to find the optimal weights between layers, i.e. W and B, that decreases the cost in the loss function. What we identify here is that, let's say this is a map of the cost function j. As we see here, it takes input W and B, and we can graph these. W is one axis and B is another axis. Right here, we can see that since this is the cost function, or basically the loss function, we have to optimize the loss function, because when we make the loss function as least as possible, that means the accuracy is the highest. And so, the goal of any neural network during backpropagation is to find that region on this map here, for example. Well, this is in 2D, most are three-dimensional, but the goal is to find this region right here down at the bottom, this red dot, where the loss function is the lowest possible, because at that point, the model performs the best. And again, loss functions can be used for tiny datasets, while cost functions are used for large datasets that are often split into batches. Again, regardless of what type of neural network you use, the goal is always going to be to try to minimize the cost function, and that's what gradient descent is used for. But let's see what gradient descent actually does, and specifically, what are gradients? This is essentially how gradient descent works. For example, we go to this last slide and we see all these massive, three-dimensional parabolas, but right here, this is just a normal parabola. And we'll try to use this as an example of gradient descent. So how gradient descent works is that it updates the weights and the biases within the model. It updates them so that we can improve them and have the best weights and biases to have the best model. As we can see here, essentially what you do is this. You take your initial weight, W, the most important part of the network, and you spin it with W minus, this is the learning rate, times D JW over DW, the derivative of the cost function with respect to W. Essentially, we just call this value DW, and if you're a little confused, we'll take a little specific example with this parabola right here. So again, back to here, we realize we want the global optimum. On this graph, the global optimum falls right in the center here, a little bit past to the right, and so basically, our goal is obviously to get there with any means possible. So, if we were on the right, if our W value, our weights, were on the right side, meaning they were more positive, well then, our slope would obviously be rising. The derivative of JW with respect to W is increasing. And when we do that, W minus our learning rate times positive value, W will obviously decrease. So because of that, you have a positive derivative, you multiply that by a positive learning rate, and you subtract W, you subtract that out of W. W is going to become smaller, so you move to the left towards the global optimum. Let's see the actual left side of the parabola too. Right here, we realize the derivative, or the slope, is decreasing, meaning that it's growing less exponentially as time goes on. The growth factor is decreasing, and so the derivative is actually negative. It's less than 0 here. So W minus the learning rate, which is always positive, and you multiply that with a negative learning rate, that's W plus essentially the learning rate, and DJW over DW. This helps us find a new W value to the right. You take W and essentially add the learning rate and the derivative. That gets us, again, to the global optimum. So it doesn't matter what side of this parabola you're on. If you use this algorithm, you'll always end up right here at the global optimum. And that's the goal of any single neural network, trying to get there. These are just math, but essentially, in any neural network, these can mostly be accompanied at a high level. You can just type in some sort of gradient descent algorithm without actually having to do any of this work in the code itself. Backpropagation, we'll put it all back together because between the front propagation and back propagation, things can get a little confusing. So, we start with the forward pass. We find the activation for each layer, get essentially the sigmoid and the tanh function, or the ReLU function. We initialize the weights W and biases B. The weights W are the strength of connections between each layer, and B is just a normal value we add just because. The activation A is what we're trying to optimize and what's passed on to every single layer. And essentially, that's what gets us our probabilities and what the model thinks is the result. This is all forward pass. What happens here, once we get that average actual cost, we see whether the model correctly identify the data set? Did it take every single data point, and did it correctly identify or do what it was supposed to do? We get a cost function and we see how well the model was doing. If the model didn't do well, well then at that point, we have to improve the model. That's where backpropagation comes in. We take that loss function and we use gradient descent to calculate the best gradients of the loss function. We go in the direction that's steepest towards the global optimum right here. And so, once we do that over a lot of time, we'll eventually reach a point at which the weights simply stop becoming better. We'll reach a point where we're so close to the optimum that if we try to train more, there simply won't be a reason to. And so, at that point, we can stop the training of the neural network, we update the weights one last time, and so we have reached convergence. Convergence is when the neural network is at its best. We've reached everything we wanted to do. We started with the forward pass, we then optimized the weights until we get the best neural network possible, and then that's the end of it. Whatever accuracy we get there, that's exactly what's going to happen going forward. And so, this is the semblance of a pure neural network. In the next video, we will look to more logistic regression neural networks and start getting coded on one of them. Thank you.